So I changed the title a little bit, but the content is exactly the same thing. Let me add to the introduction that this work is conducted at Delft University of Technology in collaboration with Angelo Simone. Let me give you an introduction to deep learning by an example from natural language processing. Say I want to translate a sentence from English to Dutch. I use Google Translate. The engine in Google Translate is a deep learning model. So I write in Google Translate, I do a ton of deep learning. Now, I would like to draw your attention to how this deep learning model translated the word ton. Ton could basically have two meanings. One is a unit of mass, and the other is a lot. What this deep learning model did was that it took a look at the words that came before ton, specifically I do, and then it made this decision that, well, the only reasonable meaning is a lot, and it rightfully translated the word ton to hail fail in Dutch. That means a lot. Now, please note that a sentence is not merely a set of words, but it's a sequence of words. Meaning of each word depends on all of the words that came beforehand. Now, let's move on to our field. In our field, we also have sequences that we want to map to the other sequence. Specifically, we have sequence of, for some problems, we have sequence of strain tensors that we are interested in mapping them to a sequence of stress tensors. These problems are, for instance, history-dependent problems. Let me specifically state the problem, concretely state the problem. Consider an FE squared multiscale simulation in which we have a macro model and a micro model. At each integration point in the macro model, we send a strain tensor to the micro model, evaluate the micro model, compute the average stress, and send it back up. This turns out to be a computationally expensive practice. The reason is that at each integration point in the macro model, we are solving a finite element simulation. And a finite element simulation that has matrix inversion and complex nonlinearities to evaluate, for instance, plasticity. We can accelerate this process by replacing the micro model with a surrogate, a deep learning surrogate. A deep learning model has mathematical operations such as matrix vector multiplication. These operations run considerably faster on modern computers than matrix inversion operations. And when it comes to evaluation of nonlinearities, well, the nonlinearities are much simpler than plasticity, for instance. Now, let me tell you specifically what kind of deep learning model I'm going to use. I'm going to use recurrent neural network. This is incidentally what is used in Google engine and Google Translate engine. Not exactly the same thing, but a variant of this. A recurrent neural network is a model that can map a sequence of strain tensors to a sequence of stress tensors. At each step in the sequence, it takes in a stress tensor, a set of history parameters, and a set of trainable parameters, and outputs the stress. If you want to use this model in finite element, we gotta have stiffness matrix too. To compute this stiffness matrix, I suggest using automatic differentiation. Let me tell you what automatic differentiation is. It's not numerical differentiation because it's exact up to the machine precision. And it is not analytical differentiation because you don't need to write down the formulas and implement them in the computer. What it is basically is just chain rule. That's what application of chain rule. From implementation point of view, if you're doing deep learning, most probably you're using a deep learning library And in those libraries, there's always an automatic differentiation functionality. So computing the stiffness matrix boils down to exactly one line of code. Now, so this is the recurrent neural network that I'm going to use, but let me tell you how to train it. First, we collect a set of data, strain and corresponding stress data. Then we evaluate the stress. What we do is that we pass this strain and these trainable parameters. I just skip the history parameters to avoid verbosity. And we make a prediction of stress. Then we measure the discrepancy between the prediction that we did and the target value that was in our train set. And then we tune W, the trainable parameters, such that this error becomes smaller and smaller. The way that we do it is that we go in the parameter space, stand on the error surface, touch around ourselves, see where is the steepest slope, and we will take a step of alpha times the magnitude of gradient towards down the hill. And we do that iteratively until we reach a point that the error is small enough. Now, let me tell you how we collect these samples. We can do two things. One is to take this micro model as a standalone program, impose some strain sequences to it, and compute the corresponding stress sequence. This turns out to be a very difficult task because the space of all possible strain sequences is very large, and sampling it is computationally inefficient, if not technically impossible. What I suggest to do instead is to collect the samples at the integration points in the macro model, or a set of macro models. In this way, we only sample the space of all possible strain tensors only at the locations that we are actually interested in. So that's data collection. I showed you a model. I told you how to train it and how to collect the data to do the training. Now let's put it in the macro model and replace it with the micro model. At first, let's zoom in on the stress update in a macro model. Classically, we pass a strain tensor at time step t and Newton iteration I, together with a set of history parameters to the micro model. And that micro model would give us this stress. What we can do to accelerate this procedure is to replace the micro model with the recurrent neural network. And there's another thing that we gotta change is the history parameters. The history parameters before were physical. So for instance, they were damage or accumulated plastic strain. Right now, they're just a set of vectors of numbers. That's it. Now let me tell you something from implementation point of view. If you have a program that's object-oriented, in a sense that at each integration point in the macro model, you assign an instance of your material class, and that material class owns these history parameters, then the implementation of recurrent neural network is plug and play. Micro model is not changed at all, and in macro model, all you need to do is to write down a few lines of code to load the recurrent neural network. Now let's go to the application of some results. Consider this object here. It's a bar. There are holes along its length. The holes penetrate all the way through its width. I assume that the length of this bar is significantly larger than its width and height. So I can model it as a one-dimensional object. And to incorporate the effect of the holes, I will consider an FE squared scheme with micro model like this. And for material class, I use Perzina viscoplasticity. Now, let me tell you how I do the sampling. I consider two macro models, one a bar without imperfection and the other one a bar with imperfection. For the bar without imperfection, I pull one end of it until it reaches a value of U max, and then push it back until it goes where it was. For the bar with imperfection, I would just pull it until it reaches a value of U max. Now, for instance, for the bar without imperfection, I consider two parameters, U max and the rate of application of the displacement. And I consider a range for each one of the parameters. Then I sample these parameters at these range and construct a set. I call it train set. For each item in the train set, I evaluate the macro model and collect stress-strain data at the integration points. Right. So I collect a data set from this model, I collect another data set from the other model, I put them together and train one single recurrent neural network. Hopefully this recurrent neural network would work both in this macro model and the other one. Now, to show the predictability of this recurrent neural network, I run these two macro models with parameters which are inside these ranges, but they are not included in the train set. First, force displacement curve. This is the reaction force at one end of the bar against the imposed displacement. We can see that we can get very accurate results compared to the reference solution, and I'm going to very cautiously give you the speed-up factor, because if you have an optimized code, this speed-up factor would go down considerably, and if you have a more complex micro model, then the speed-up would go up. For our implementation and the problem that I showed you right now, we gained 1,000 times faster simulation. Now let's look at the results of the bar with imperfection. We get very accurate results for average response of the system. Force displacement curves are kind of average. To look at the element response, I plot the strain fields. And we can see that our recurrent neural network can very accurately predict this localization in the strain field as well. Now, allow me to conclude my talk by saying that there are difficulties when using deep learning. One is that the development process is very time-consuming. It has a lot of trial and error until you reach a model that actually gives good results. The other one is that the deep learning model is basically a black box. So if your model is doing very bad predictions, it makes very little sense to take a look at the parameters. It probably wouldn't tell you much. And the third thing is that the results that I showed you, that everything was on top of the other, it was when the parameters were inside the training range, the range that I trained the model on. So soon as we go outside that range, then the results become very inaccurate. Now, I have a list of ingredients that I think they're essential into success. One is the thing that people observed in practice, that the more data you feed to your model and the bigger you make your model, the performance of a deep learning model keeps increasing. That's pretty much why it becomes so famous, because most other machine learning models, the performance stagnates after adding more data, as if it doesn't know what to do with the rest of the data. The second thing is scalable software. Well, hopefully there are so many of them available right now, and they're open source, they're free to use. In this work, I used Google's TensorFlow. The other thing is affordable hardware. You see, the training process is expensive, computationally expensive, so we need powerful machines, but there are a lot of trials and error as well, so we need those powerful machines to be affordable. Thanks to cloud computing, now we can rent pretty good machines that are also affordable. In this work, I partly used Google Cloud. And at the very end, I want to emphasize that whenever people talk about deep learning, they talk about amount of data. I don't think it matters that much so much as availability of data is important. Allow me to leave you with this thought that just imagine that I didn't do the problem that I showed you in my talk, and I would have gone to a very fancy lab and collected data there. Came back with a bag full of hard drives, full of data, trained the deep learning model, just to realize that in a certain range of parameters, my model doesn't do well. So what I have to do, there's just one thing to do. Go back to the lab, collect more data, and come back. Now, my question is that, how on earth am I going to persuade Angelo Simona to pay all the money so that I can do that? Let me thank the people who help us keeping the lights on at ERC. And that's all. Thank you very much.